Welcome to this lecture series in real analysis. In this lecture, we'll prove a very interesting theorem, which is the inverse function theorem. And we will use mean value theorems on the way. So let's recall the most basic one, Rolle's theorem. So what does it say? It says that suppose we have a continuous function defined on a closed interval a comma b, and it is the function is assumed to be differentiable in the open interval a comma b. Further, if we assume that f of a is equal to f of b, so if f of a is equal to f of b, then Rolle's theorem says that the derivative of the function vanishes somewhere in the interior of the interval. I'm not writing it out, but I hope you recall. Okay, then we also need this fact that if suppose I is an interval and we have a continuous function defined on it, then the image of the interval under our function is also an interval. It may be an interval of a different nature. For instance, you may start with an open interval, but here the image might be a closed interval. That can happen. However, this is something that perhaps I never explicitly proved or gave as an exercise before. I don't recall. What is it? Suppose I is an open interval now, and assume f is an injective continuous function. Then we know this is an interval by the previous thing. We don't even need so much hypothesis. But with this extra hypothesis, we can claim that the image is actually an open interval. So the image, or rather, how shall I say it? Injective continuous image of an open interval is all that I'm saying. So please do this exercise, we will use it. Lastly, there is a theorem that we proved earlier, is that again, we have an interval I, and we have an injective continuous function defined on this interval. Then the inverse is also continuous. So image of I is also an interval, that's okay. And the inverse is also a continuous function. Okay. Here are some problems for practice. And now let us get started. So first we will prove what I will call the intermediate value property of the derivatives. And I think it is a fact due to Darboux. We will later encounter another theorem due to Darboux when we will discuss integrations. But for now, we have this theorem. What is it? So suppose f is a differentiable function. And when we say f is differentiable, of course, on the left end point, we mean it is right differentiable because there is no such thing as the left derivative at this point. The function is not defined towards the left side of this point, so there is no question of the left derivative. And we also similarly assume that the function is right differentiable at b. The function is left differentiable at b. The function is right differentiable at a and left differentiable at b. And everywhere in between it is differentiable, meaning it has a left and a right derivative and the values of the derivatives agree. Fine, so I'm sure you know what this means. And now suppose lambda is a real number which is sandwiched between these two derivatives. So when we write f prime a, we of course mean the right derivative at a, and f prime b refers to the left derivative at b. So lambda is a real number sandwiched between those two. Then the claim is that there is some c strictly between a and b, such that the derivative at c is equal to lambda. So if a differentiable function assumes, or rather if the derivative of a differentiable function assumes two values, then it also assumes all the values in between. Just like in continuous functions. The continuous functions also have this property. If you have a continuous function and it achieves two values, alpha and beta, then it also achieves every value in between. So this property, this intermediate value property, is enjoyed by derivatives of differentiable functions, is what we are stating here. This is not to say that the derivatives of differentiable functions are continuous. You can have a differentiable function with discontinuous derivative. We will perhaps look at an example later at some point. All right. So how do we prove this? I will not write the details, I will just say it. The first reduction would be lambda equals 0. So we will just explain the proof when lambda is equal to 0. If lambda is non-zero, or what I'm saying is just you can reduce to this case by defining another function g by writing gx as fx minus lambda x. That's it. So you can reduce to the case where lambda is equal to 0. Okay. So if lambda is 0, what does this say? It says that this is negative and this is positive. So pictorially, what will it look like? We have a and b here, and there is some value at a, some value at b. And since the derivative at a is negative, because we have assumed that lambda is 0, what will be the right derivative? It will be some, or whatever, what will be the right tangent at the point A? It will look something like that. And similarly at B, the left tangent will look something like that. Now by our geometric definition of derivative, there is a cone here such that, or whatever epsilon you make and whatever epsilon you choose and make the epsilon cone, we know by definition of derivatives or by definition of the right tangent that there is some neighborhood here such that the function is entirely contained in this neighborhood, in this cone, if you choose points in this neighborhood. Similarly, if you choose any epsilon, the same thing happens for this cone. So just choose very small epsilons so that what happens? So that this is negative and this is positive. What do I mean by that? This is negative meaning the slope of this is negative and the slope of this is positive. This has positive slope. We can just choose a small epsilon so that the upper part of the cone also has positive slope. And similarly here, since this has negative slope, we can choose an epsilon so small that this has also negative slope. Now, there is a neighborhood such that whenever we choose a point here, the corresponding point in the graph is within this cone. Similarly, there is a neighborhood here with the same property. So what we see is that the function decreases, at least for some time. The value of the function at a is something, but because of this cone business that we just said, we see that at least for some time the value of the function will be less than this, and at least for some time the value of the function will be less than that. So now, since f is in particular a continuous function, f is a differentiable function, so in particular it is a continuous function, and hence it achieves a global minimum because this is a compact interval. So f has a global minimum somewhere. And because it decreases from a, and also, towards, if you come to the left of b, it also decreases. The global minimum has to lie somewhere in strictly between a and b. The global minimum cannot be at a or b. So all of this reasoning says that f achieves a global minimum somewhere strictly between a and b. And wherever that is, the derivative there will be 0. The derivative at any local extrema is going to be 0. And therefore, at any global extrema, the derivative is also 0, and that's it. So that's the proof of this theorem, that the derivatives of differentiable functions have the intermediate value property. Very nice. And now we can go to the inverse function theorem. So what do we have? We have a function defined on an open interval this time, and assume it is differentiable, and also assume its derivative never vanishes. Okay. Then we will show that f is injective. Image of f is an open interval. And most importantly, those two things are easy to show. This is also easy but very important, that inverse of f is also differentiable, and its derivative can be computed via this formula. So the derivative of the inverse at the point y is the derivative of the function f at the point f inverse y. Right? So these 4 things we want to establish. Let's do these two without any writing. So why is f injective? Well, if f were not injective, then by Rolle's theorem, it has to have a zero derivative somewhere. It is a differentiable function. If it is not injective, it takes the same value at two different points, and then Rolle's theorem kicks in, and then this hypothesis would be contradicted. So the injectivity of f follows from Rolle's theorem. Now, image of f is an interval. That is clear because f is a in particular continuous function. But why is it an open interval? Just look at the exercise that I left you in the recap section. We have an injective continuous function. We just showed it is injective. So we have an injective continuous function defined on an open interval, and hence its image is also an open interval. This is precisely the exercise that I left you with. So this is also done. So now the point is to show 3 and 4. And in the course of showing 3, we will already show 4. In fact, just as a side remark, if you know 3 to be true, you can show 4 by using the chain rule also, but we would not need it. So let's start with the proof. And the proof is actually very, very simple. So let's maybe develop a notation. Let's write G in place of F inverse. And we've already seen that F is injective, so maybe just for sake of visual convenience, let's draw something. So let's say the function's graph looks like this. Since f is injective, it is also going to be a strictly monotone function. And we are, without loss of generality, assuming that f is strictly increasing, because you can give the same proof when f is strictly decreasing. So injectivity of f, injectivity and continuity of f, but I'll just say injectivity of f implies f is strictly f is strictly monotone. And without loss of generality, assume f is increasing. And I have drawn a graph just for understanding the thing visually. Okay, now we want to show that this inverse function is also differentiable. So pick a point y star in the image. And let's say image is this open interval. So let me mark that out also. That point is C. And that point is D. And we have chosen some point y star. Yeah, so we have chosen some point y star in the open interval C, T, meaning in this region. And we'll just show that G is differentiable at the point y star. So to do that, we are interested in showing that this limit we want to show that this limit exists, and to prove 4, we want to show that limit is actually equal to that thing that will automatically follow. Yeah, so how do we show that this limit exists? How do we show this? So pick a sequence, yn be a sequence in the domain of the function g, such that yn converges to y star, right? And now, suppose yn is somewhere here. If that is yn, then we have a corresponding point. We have a corresponding point xn. And let us also mark out the point corresponding to y star. So here we have x star. Okay. Now, this function g is the inverse of of an injective continuous function on an interval, so G is continuous. So here itself I should have written that, note that G is continuous. We recalled this in the beginning. The inverse of an injective continuous function defined on an interval is also continuous. Okay, so G is continuous, and therefore since Yn converges to Y star, Xn converges to X star. X star is nothing but, just for clarity, X star is nothing but G of Y star. Right, so the continuity of G immediately shows us that since Yn converges to Y star by choice, Xn converges to X star. Alright, and now we can just talk about this limit. So there is just a lack of space, but I'll try to make space. So what is this limit? This is, or let's just talk about this limit where we use the sequence Yn. Right? We wanted to understand the existence of this limit. So to understand the existence of this limit, we can just choose a sequence that converges to Y star and plug that in here in place of Y. So this is what we are interested in showing, that it exists. But what is it? This is equal to xn minus X star divided by f of xn. Sorry, this was a Y star here. Yeah. So we have done nothing. It's just xn by definition was g of yn, which is same as saying that f of xn is yn. F of xn is yn, or you can say g of yn is xn. Same thing. So we haven't done anything so far. But if you look at this thing inverted, if you make this the numerator and that the denominator, that limit exists because f is a differentiable function. So what is this? This is limit of 1 upon f of xn minus f of x star divided by xn minus x star. Right? But 1 upon x is a continuous function. So this function x going to 1 upon x is a continuous function. And what is this thing? This is the value of this expression fed to this function. And continuity of the function just says that the limit pushes inside. So without giving too many details, I'll just write this as equal to the following. This is equal to limit n going to infinity. Right, I hope that is readable. So limit kind of pushes inside, and this we know exists, so therefore this guy exists. But what is this? This much is equal to the derivative of f at x star. So this whole thing is 1 upon f prime x star. So I'll write the conclusion here. What we have shown is limit of n going to infinity g y n minus g y star divided by that thing. This is equal to 1 upon f prime x star. This shows that g prime y star is equal to 1 upon f prime x star, but x star we can write as f inverse of y star. And instead of g, we can write f inverse. So this is exactly the fourth conclusion. The third one we already proved. As soon as we showed this limit exists, we proved the third one. But the fourth one also follows by the same line. So very simple. The proof is very simple, but the theorem is quite powerful. So now let's see an application. So we have some positive integer, and we have this function defined as the nth root function. This is a well-defined map because we are only taking positive inputs. So if you feed a positive input, this is a well-defined thing. And previously we have seen that this is a continuous function because it is the inverse of an injective continuous function. Which function? It's the function that takes x to the power n. So this is an injective continuous function and therefore its inverse is also continuous. So we know g is continuous, but now we are saying more. We are saying that it is also differentiable. And further, you can compute the derivative via this formula. So the proof is essentially the same as it was for continuous functions. We just define this map, which I just wrote. So define this map as fx equals x to the power n. And we know it is differentiable. It is indeed a polynomial function, so it is differentiable. The derivative never vanishes. So Alexa, stop. So the derivative never vanishes. And now you can just apply the previous theorem. The inverse function theorem shows that g is differentiable. And in fact, the derivative of g at any point y is this thing. And if you use this, you will get the correct thing. So very nice. We can compute derivative of surds now. In fact, for the first time, we know that surds are also differentiable and we can compute their derivatives. All right. Lastly, one simple example. So suppose we have this function f given like this strange fashion. Then it is a differentiable function because it is the composite of two differentiable functions. The thing inside is a polynomial that is differentiable, and we have just composed it with the square root function, which we just saw is differentiable. So this guy is also a differentiable function. And you can compute the derivative by using chain rule. Maybe I'll do it. So what is f prime x? F prime x would be, by chain rule, the derivative of the square root function is 1 upon twice of root of x, but here in place of x I will feed this thing, and then I'll multiply that by the derivative of the polynomial that we have. So just a very simple exercise in chain rule. Figure this out if it is unclear. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.